Hello and welcome to my second channel. And as I promised on my main YouTube channel, I will create this one where I've been doing some live coding or actually studying. And the first sequence of the videos that I want to do is, I would call it Let's Learn. And we will study the neural networks from the scratch. So there is a book called Neural Networks from the Scratch in Python. And I want to go through this book, and it's actually a pretty big book with lots of the explanations of what the neural network is. And I want to dive into the topic of the neural networks more with you. I have some exposure to neural networks in general because I used to port them to the mobile devices, but I was on the side of running the inference, like the actually using these models on the mobile devices, which has its own limitations and interesting challenges. And I passed and I took the Fast AI course some time ago. But for example, the core with the mobile development, I already used the implemented neural network, and with the Fast AI course, I just use Python and libraries like the Fast AI to implement any neural network. But the goal of this book is actually to implement like purely from the scratch. And one of the things that I'm not going to do this in Python because it will be way too easier. I'm going to do this with the golang. And there are a couple of reasons. The first one is that I want to practice golang more. I did some small pet projects and that's it. And the second one is I want to really dive into what a neural network is, how the code is written to train and do the inference and write everything, well, as much as possible from the scratch. There will be some challenges with this book because it's written with the Python and it uses the NumPy a lot. And NumPy provides you a very convenient way to work with the matrices and like tensors and so on. So we will need to rewrite or at least find some alternative in a Go. Probably we'll need to write some things from the scratch. So that's the goal. And like the main goal of and it should be and it will be a long series of the videos, because you can see that there are like 666 pages. Well, that's the devil number, but okay. Hopefully it's not a coincidence. In this book, I didn't have enough sleep. There are more than 600 pages in this book, and I want to have these like around 1 hour long videos. And the reason I want to show is that you can learn practically anything if you will show up and actually do stuff. So this is why my plan, at least for now, let's see how it goes, to record 1 hour of the study by this book, like reading, trying to understand, explaining out loud what are my thoughts, and writing the code with this book, and go on together. Again, this is the Neural Networks from Scratch book. Highly recommend checking it. I bought this book. If you want to actually study this and learn the neural networks from the scratch in the Python, I would highly recommend to buy this book, because here we will go, here you will see my ways of learning, and in some cases I will be probably quick because some parts will be easier for me to understand. In some and on some parts I will be, stupid enough and learn something for a long time, or maybe skip some parts because I'm not that interested in them. So don't forget to check this book. But for now, let's go. Chapter 1. I don't remember. Let's take a look how many chapters we have. I think this one, table of content. Okay. Yeah. Introduction into neural networks. I think this video will go through this chapter and read what an actual neural network is. Chapter 1 is actually coding our first neurons. I think I will do it tomorrow. And there are other like adding layers, activation, so we will go over everything later. So let's start. We begin with a general idea of what neural networks are and why you might need be interested in them. And actually find this image pretty interesting because I tend to see people thinking about machine learning, which is, this second circle, as a deep neural networks. I think what we will do here, it will be neural networks, but we will see, and there is a difference. But machine learning in general is not only about deep learning, where you learn in this neural network. There are other algorithms in machine learning. Okay, and there is just a music outside. I hope you don't hear this. A brief history. I will skip it for today. I mean, if you want, you can buy the book and check it. What is the neural network? Artificial, and this is pretty important. Artificial neural networks are inspired by the organic brain, translated to the computer. It's not a perfect comparison, but there are neurons, activations, and lots of interconnectivity, even if the underlying processes are quite different. So this is on the top. I think this is the example of the neural networks in the brain. I don't know half of the terms, but this is on the bottom. This is the neural network that we're going to implement. And well, we can say that they kind of similar, because we have the neuron. I think this is the neuron 2, this one. This is our artificial neuron. There are inputs, like lots of the inputs into one. And then, when you watch some videos about the biology and the studies about the brain, they can tell that, for example, this part of the brain is responsible for the fear. And I understand it like this, that if something happens and your brain analyzes lots of the inputs that you have, like visual, audio, etc., and specific parts of the brain gets activated. So this is why we can see like some parts of the brain kind of highlights. And as far as I understand, the idea of the neural networks in the machine learning is the same. And I guess we'll talk about this later, but for what I know from now, that each neural network has its own activation function, and it means that there are conditions based on the input and the type of the neuron in which the neuron gets activated and it propagates the information further. But we'll see. A single neuron by itself is relatively useless. Okay. But when combined with hundreds or thousands of other neurons, the interconnectivity produces relationship and results that frequently outperforms any other machine learning method. This is what I've been talking about. There are other machine learning methods. So building the neural network or AI how it's called today, it's not only the part of the machine learning, but probably it's the most not efficient, but not more complicated. I think it's the most interesting in terms of the results, because, well, the general idea of the classic software is that you have an input, you're building the rules, like all of the code that we're writing is just a set of the rules. Yeah, it could be pretty complicated rules, but still it's just a set of the rules. And it defines the output. But with the neural networks, the way that neural networks are implemented is you have the input, you have the output, and the process of learning is actually the process of creation of these rules. So these neural networks, for example, this is an example of neural network with 754 parameters. I don't know how much neurons are here. Oh, yeah. We have, for example, 10 inputs, 2 outputs, and 3 layers by 16. So it's like 48, 48 neurons. And the process of training those models is actually to create this set of the rules. And the better we have this combination of input and output, the better will be the model, meaning that the better rules will be created. Example of neural network with 3 hidden layers of 16. Yeah. The above animation showed the example of the model structures and the numbers of the parameters. The model has to learn, this is the important part, to adjust in order to produce the desired output. The details of what is seen here are the subject of the future chapters. Okay, let's take a look. Well, actually, animation is different, but oh, okay, no, it's the same. So what we'll have, one will need to create bigger models. Okay. Well, this is actually pretty big already. Okay. So we have 10 inputs. I don't know what it will be. And we have 2 outputs. Yeah, we have the same 10 inputs, 2 outputs, and 3 layers with a huge amount of the neurons. And they all, it's even impossible to see if there is somewhere an output for this. And it's just 34,000 params. And right now think about something like ChatGPT with billions of the params. I mean, how complex those models are. Let's go. It might seem rather complicated when you look at this. At it this way. Neural networks are considered to be black boxes, in that we often have no idea why they reach the conclusion they do. We do understand how they do this. And this is what happens during the model training, because you're given first you actually need to create the architecture of the model. And the model architecture will influence the task that it can perform, because there are, for example, transformers, which is the GPT, like the ChatGPT. It uses the GPT acronym, which is pre-trained general transformers. And I know that the transformers is one of the models architecture that boosted the work with the text. For example, there are other models, like type of the models, for example, the convolution neural networks, which pretty commonly used for tasks around images. For example, the image classification, or I don't know, I think you all saw, like in the programs like Zoom or FaceTime, there is a blur. And how it usually works, it takes the image, it passes it through some neural networks that detects where there is a person and where is the background, and it returns the mask, like image mask that you can apply, and then you can split the image into two parts, the frontmost image and the background. And this is like part of the convolutional neural networks. Dense layers, the most common layers, consist of interconnected neurons. I think this is what was shown here. So we have the interconnected neurons. Because, for example, take a look at this one. It connected with this one, and this one, and there should be a line here, here, and all of the neurons in these layers, in this layer connected with this layer, and so on and so on. And here's the same with the input and the output. Each connection between neurons has a weight associated with it, which is a trainable factor of how much of this input to use. And this weight gets multiplied by the input value. Once all of the inputs weights flow into our neuron, they are summed, and a bias, another trainable parameter, is added. The purpose of the bias is to offset the output positively or negatively, which can further help us map more real-world types of dynamic data. In chapter 4, we will show some examples of how it works. Okay, the concept, I do understand the concept of the weights, but I was always wondering, why do we need the bias? Because from what I understand, we have an input, this is some value, and then, for example, we have a neuron. We have a neuron, and we have the weight of this connection, which I would say it's a proportion of how it will contribute to the result factor. To the results. For example, in some cases, this neuron will have the most important, let's say, role based on the input, or in some cases it will be deactivated and not used at all. For example, if you can think that, for example, this is the model that will determine numbers, the recognition of the numbers. Some neurons can be activated if you have a straight vertical line, for example, for number 1. Or other parts will be activated if they have a round at the top of the number, which could be a sign of 8 and 9. But with the bias, maybe it's a way to, tweak somehow the model, but I hope we will see how it works. That we can tune to fit our model to the data. In a neural network, we often have thousands or even millions of this parameter tuned by optimizing during training. Some might ask, why not just have biases or just weight? Biases are weights of both tunable parameters, and both will impact the neuron's output, but they do it in a different way. Okay, since weights are multiplied, they will only change the magnitude of, or even completely flip the sign from positive to negative, or vice versa. Output equals weight multiplied by input plus bias. It's not unlike the equation for the line. Yeah, it's a straight line. We can visualize it. Okay, and if we take a look, like the weight, since it's a multiplier, it can go, well, first it changes the magnitude. Like you can see the angle gets different. And I think that it means that it could change drastically the importance of this neuron. Yes, and based on the param and based on the weight, it can be negative. But here's the bias. And here we have this, for example, the same angle as we have in the first example. How about the bias parameter? The bias offsets the overall function, for example, with a weight of 1 and a bias of 2. As we increase the bias, the function output overall shifts upwards. If we decrease the bias, then the overall, okay. If we increase the bias, it will go top left. If we decrease, it will go bottom down. But as you can see, weights and bias help to impact the output of the neuron, but they do so in a slightly different ways. This will make even more sense when we cover the activation functions in the chapter 4. Okay, because for me right now it's still not clear, like, how they will be changed. I mean, in which cases the model will change the bias, and in which case model will change the weight. Still, we can already see the difference between weights and biases and how they might individually help to influence the output. Why this matters we'll convey shortly. Okay. Okay, so this is the neuron. It has weight and it has bias and input. Input can be the original input or input from the previous neuron. Hmm. Yeah, as I understood, the ReLU is this activation function, but we'll take one. As a very general overview, the step function meant to mimic a neuron in the brain, either firing or not, like an off-off switch. In the programming, an off-off switch as a function would be called a steep function because it looks like a steep if you graph it. Okay, so for a steep function, if the neuron's output value, which is calculated by sum, so we have, for example, here we have, here we have inputs from all the previous layers, and we still have it, for example, we have a value here, it's multiplied by the weight plus some bias that is assigned to this neuron. And we do this for all of the previous layers. Then we sum up it, and that will be our value for the neuron. This is at least what I understand. However, we need to understand if this neuron gets activated or not. For steep function, if the neuron's output value, which is calculated by sum, bias is added as the last step. Okay, so it's actually we are summing all of the inputs multiply it by weights, and then we add a bias in the end. And if it's bigger than 0, then the neuron fires. Otherwise, it doesn't fire and would pass along a 0. The formula for a single neuron might look something like. Okay. We then usually apply an activation function to this output, noted by activation. While you can use a step function for your activation function, we tend to use something slightly more advanced. The neural networks of today tend to use more informative activation functions, such as a rectified linear activation function, which we'll cover in depth in the chapter 4. Okay, I cannot wait for chapter 4. Each neuron's output could be a part of ending output layer as well as the input to another. Okay, so it could be the transfer into the output or to another layer of neurons. While the full function of the neural network can get very large, let's start with this simple example with 2 hidden layers of 4. We have 2 inputs, 2 outputs, and 8 neurons in total. Example of the basic neural network. Okay. Along these 2 hidden layers, like this is the first one, this is the second one, and I mean, my understanding why they called hidden layers, because when you use a neural network, you interact with the input because you pass some data to the input, and then you read the output. And you don't interact with the layers in between at all. This is something that is happening during the prediction phase, and you as the user of the neural network don't deal with this at all. Along with these 2 hidden layers, there are also 2 more layers here, the input and the output. The input represents your actual input data, for example, pixel values from the image. While this data can be raw, in the exact form it was collected, you will typically pre-process your data through functions like normalization and scaling, as your input needs to be in a numeric form. Yeah, for example, when I worked with the images, usually images are stored in the memory as integer values from 0 to 255. But neural networks works with float numbers from 0 to 1. So for example, like the color in between, well, for example, 255 should be 1.0, because you can do something like, I don't know, you have a shade of the color like this, then you multiply it by 255, and that's your float number that you will pass as an input. And I know that, for example, when you work with the models for the text, for example, the text prediction, when you type something on the keyboard, you don't pass the text itself, and you don't pass the, for example, ASCII number of the text. There is a methods when you have to create something called like a dictionary, and every part of the word, or maybe the whole word, will have its own number, and then you pass the sequence of the numbers that, well, represents nothing meaningful to you, but along with the dictionary you can pass those numbers into input. Then you can take the output with the same numbers, and then you can decode it into some meaningful text. Concepts like scaling and normalization will be covered later in this book. Yeah, however, it is common to preprocess data while retaining its features and having the values in the similar ranges between 0 and 1s, or -1 to 1. To achieve this, you will use either or both scaling and normalization functions. The output layer is whatever the neural network returns. And this could be different. For example, here, I think it's described here, it could predict two classes like dog, a cat. Well, yeah, maybe you could have a neural network that predicts just dog and not dog, but it doesn't matter right now. But here it will return a probability from 0 to 1 if it's a dog or if it's a cat. So for example, for some images, it could not be that clear. And for example, it will return 50% that it's a dog and 50% that it's a cat. I would like to see this animal, but still. Yeah, and this is an example of the data. For example, this is an input image. And with the dots, I think it represents the raw image data, because usually you just pass all of the bytes into the neural network. And then I would say that, for example, these solid circles represents the activations. For example, maybe there are some features, for example, I don't know, just imagining. For example, this one understand that this is I don't know, the dog's eye. I don't know, something like this. This was, for example, and this was not activated at all. Maybe it didn't find the mustaches of the cat. And then there's a sequence of the activations that led to the dog. For each image passed through this neural network, the final output will have a calculated value in the cat output neuron and a calculated value in the dog output neuron. So it's not like it tells you, like even with the binary classification, it tells you not just yes or no. It returns the probability, like the number of how confident the model is. And for example, it could be that the probability here is something like 90% or 95% that it's a dog. And it means that the model is very confident, but it's for us to how to call it? It's for us to understand or define this low value when we think that it's okay. The thing that makes neural network appear challenging is the math involved and how scary it can sometimes look. For example, let's imagine a neural network and take a journey through what's going on during the simple forward pass of the data. And this is how, well, at least from what we saw before, like every network, like every neuron has to sum up the data, but then add bias. And I think this is this part, for example. What I can see, it takes 0, then it sums all of the, I would assume that it's the input weights multiplied by weights plus bias. And then probably this is the same, that's what it was shown before, the activation function, when it uses the max and returns 0 if it's below and returns the value if it's, well, greater than 0. And then I believe it represents all of the, so I think that I assume this is the first layer, then this is the second layer because it's based on the first layer. This is the maybe third layer or even the last one. Like full formula for the forward pass of the example. Okay, we have animation. Let's take a look. Okay. Yeah, I was correct. X is an input. Yeah, so these will represent the first hidden layer. Z, I would assume that this is the okay. way too quick. Okay, I guess that it was a concrete neuron. Y first is the first layer, Y second is the second hidden layer, and yeah, it uses X1 as the first input, it uses X2, I think this is the input as the from the previous layer. Yeah, and then I think this is then the activation function, which we will understand hopefully later. Okay. I still don't understand fully this part and the division, but you know, the top part is yes. Naturally, that looks extremely confusing. And above is actually the easy part of the neural network. This turns people away, understandably. In this book, however, we're going to be coding everything from scratch. And when doing this, you should find that there is no step along the way to producing the above function that is very challenging to understand. Okay. For example, the above function can also be represented in a nested Python function. Yeah, again, I still don't understand the why do we need the logarithm here, and the dot product. Probably this is this real function, but we'll see. But for example, maximum between 0 and sum. Oh, this is the dot product. Okay. But okay, that was promised that we will implement this from the scratch. So I think that will be the second part of the book or second chapter. So we'll see. There may be some functions that you don't understand yet. For example, maybe you don't know what a logarithm function is, but it's something we will cover. Then we have a sum operation and exponenting operation. Okay, yeah, but we'll go through this. Okay. A typical neural network has thousands or even millions of adjustable parameters. By the way, the parameters they called weights and biases. Okay, and I guess during the train process, because we have the input, we have the output, and we have the model architecture. So all of these neurons and what they does, because it's not like every neuron has the same activation function, as I know that they could have very different functions. And what they do, maybe some of them sum up the inputs, some of them, multiply it and take the square root. I don't know. But the unknown things during the model training will be actual weights, so the connections between neurons and the biases of each neuron. And the model process should change specifically this. The end goal of the neural network is to adjust their weights and biases. So when applied to yet unseen example in the input that produce the desired output. So the idea that, for example, we have 100 images of the cats and dogs. We'll train on 80 images and we will leave 20 as the test data. And the assumption that you train the model, then you take this 20% and you can pick up any image from this data and the model should predict it correctly, mostly. One major issue with the concept is overfitting, when the algorithm only learns to feed the training data, but doesn't actually understand anything about underlying input-output dependencies. And I mean, here it's written as the main issue, and as far as I understand, in general, it's an issue. But for some tasks, I know that the overfitting is a good thing. because the goal is for model to not create the new rules to make the predictions, but actually to learn the train data set. I know, well, as far as I know, that it started to be used more commonly, but still the overfitting is a problem, because the general idea of the neural network is to kind of learn the rules and learn the connection between the input and the output, so it can be reused on unseen data. Okay, this is actually, we're going to the chapter 4, and how long? Okay, this is 42 minutes. Okay, let's check the rest of the chapter 1 and we'll finish for today. Overfitting. The network basically just memorizes the training data. Those we tend to use in-sample data to train a model and then use out-of-sample data to validate an algorithm. Certain percentages are set aside for both data sets to partition the data. For example, if there is a data set of 100,000 samples of the data and labels, you will immediately take 10,000 and set them aside to be your out of the sample or validation data. This is what, for example, from the FastAI course, I know that you have a data and you split it into the training set and the validation set. And the process is like, there is a epoch of the training, then you use the validation to check how good the model is, and then you go to the next epoch. You'll train your model with 90% of the data, and then you use 10% of the data to check it. I remember in the FastAI course it was 20%, like 80-20, but I guess it's up to you. And probably it's based on the amount of the data that you have. The goal is for the model to not only accurately predict the trained data, but also to be similarly accurate while predicting on the withheld out of the sample validation data. This is called generalization, which means learning to fit the data instead of memorizing it. And I remember in the FastAI, there were charts that will show you the overfitting. But okay, probably it will be described here. The idea that we train slowly adjusting weights and biases a neural network on many examples of the data. We then take out of the sample data that the neural network has never been presented with and hope it can accurately predict on those data too. So I guess the process is like this. You train the model, you show it the validation set, you estimate or you calculate the accuracy of the prediction, and the more you train, the more this accuracy will go up. But with the overfitting, if you train for too long, the accuracy will go down because it will learn the training data more and it will start to produce worse results on the unseen data. I think this is the way you overfit already, because the accuracy will actually go down. But as much as the accuracy goes up, it means that you train your model better and better. At least this is what I understand. You should now have a general understanding of what the neural networks are, or at least what the objective is and how we plan to meet this objective. To train these neural networks, we calculate how wrong they are, using the algorithms to calculate the error called loss, and attempt to slowly adjust the parameters, weights and biases, so that over many iterations, the network gradually becomes less wrong. The goal of all neural network is to generalize, meaning the network can see many examples of never before seen data and accurately output the values we hope to achieve. Neural networks can be used for more than just classification. They can perform regression, like predict a scalar singular value, clustering, and many other tasks. Classification is just a common task for neural network. Yes, but I mean, if you think that, well, okay, this was the first chapter of the book. This is just an introduction. We didn't write any of the code, and in the chapter 4, I will do it tomorrow. I will start doing tomorrow. We will start coding our first neurons. And meanwhile, I know NumPy a little bit, and this is the library to do some matrix multiplications and so on. I mean, it's very highly optimized library for the Python, mostly written in C with the bindings for the Python. And it's very convenient. And the second one is matplotlib. It's used to draw like stuff on the screen, like the data on the screen, functions, etc. So I will find alternative to this. I know that there is no direct alternative for the NumPy in Go, but there are some close things. But I will check, and I will start doing it tomorrow. So thank you for watching, and see you tomorrow.